Well, thank you all for coming today. It's my pleasure to introduce Michael Carls, presenting on modeling one-dimensional groundwater flow revisited.
Thank you. So I'm going to talk about a revision to a project that actually appears in the Simio modeling scenarios. Okay, so in a modeling scenario, modeling one-dimensional groundwater flow, a mathematical model for one-dimensional flow of groundwater through an aquifer is developed and investigated by means of data collected from a physical groundwater flow model. And for this investigation, it's assumed that the head levels, which is essentially water levels at each end of the aquifer, are fixed. And so suppose that instead of boundary conditions that remain fixed for all time, the head levels at one or both of the boundaries of the aquifer can change with time. And so we're going to develop a model for this new situation and use data collected from the physical groundwater flow model to investigate this new model. Now, so this talk is actually kind of complicated, so I thought it'd be good to give an outline of what you're going to be seeing here. So first, I'm going to look at some groundwater basics like aquifer, Darcy's law, hydraulic head, the idea of continuity, which is conservation of mass, develop a groundwater flow equation, look at a physical sand tank groundwater flow model, and then talk about how to collect data from that. And then we're going to look at the Simio groundwater flow model scenario that actually appears right now. And we'll develop a fixed head level model for that and then test our fixed head level model. And then we're going to look at a revised groundwater flow modeling scenario, and we're going to develop a time-dependent head level model and then test the time-dependent head level model. Okay, so first of all, this guy is pretty famous when you're looking at modeling groundwater. This is Henry Darcy. And in the mid-19th century, the city of Dijon, France, decided to improve and enlarge the city's public waterworks. And Henry Darcy, he was the local inspector general of bridges and roads, and he was responsible for the civil engineering program. And one of the challenges faced by Darcy was how to design sand filters for the city's public fountains. And sand is an example of a material found in an aquifer, which is a body of saturated rock through which water flows easily. And if you click on this link here, there's actually a video about Henry Darcy you can find on YouTube. This is something I show to my class when I teach this stuff. Okay, now there weren't any models for the flow of fluid through a porous medium, so Darcy had to create one. And to do so, he performed his own experiments on the flow of water through sand. And his results, including what we now know as Darcy's law, were published in 1856 as an appendix to a 647-page report on the project Le Fontaine Publique de la Ville de Dijon. Okay, so using an experimental setup similar to the figure to the right here, Darcy determined that for one-dimensional flow, the volumetric flow rate of water, which we call Q, varies jointly with respect to the hydraulic gradient I and cross-sectional area A by means of this formula here. This is Q is K times I times A. The equation 1 is known as Darcy's law. And this proportionality constant K is called the hydraulic conductivity, and that depends on the geologic material through which the water is flowing. And the hydraulic gradient measures loss in hydraulic head. Hydraulic head loosely is defined as the height of the water
Missed the sound of that.
relative to a reference point over a given distance L. Okay, if you look at figure 2, hydraulic gradient is a change in head level over the distance between the 2 points we're measuring the water levels at. And if we label x1 as x and x2 as x plus delta x and consider head drops over shorter and shorter intervals, so by this we mean let delta x go to 0, the hydraulic gradient can be written in differential form as a negative dh dx. And the minus sign means you're flowing from high water levels to low water levels. Now, the units of Q are volume per unit time, and hydraulic gradient is dimensionless, so it follows that the units of hydraulic conductivity K are length over time. Okay, so let's consider an aquifer with fixed head levels at each end, such as the one depicted in figure 3. And we'll assume the aquifer is made up of homogeneous material and that groundwater flow through the aquifer is one-dimensional. By that, I mean horizontal. And with these assumptions, we can consider the head level H in the aquifer to be a function of position along the x-axis and time t. So H is a function of x and t. So this figure 3 shows water flowing from right to left through the aquifer. So we're assuming the head level H1 is greater than the head level H naught, along with a small representative element of which delta X in cross-sectional area A. So if we use Darcy's law and the idea of continuity, which is another name for conservation of mass, we can derive a partial differential equation that describes hydraulic head level H of xt at any point in the aquifer at any time. Okay, there's 4 possible contributions to flow through this representative element. So there's flow across the right face, flow across the left face, flow introduced from an external source, and flow released from or contributing to storage within the medium itself. So as defined above, Q of xt, that's the volumetric flow rate. That means the volume of water per unit time, with units of Q being volume over time. And typically, volumetric flow is, if it's bigger than 0, that indicates flow in the positive x direction. So we introduce the negative sign to indicate groundwater is flowing in the negative x direction. And this term R of xt, that's often called recharge. And in groundwater flow scenarios, it can be related to precipitation or leakage into or out of the medium from layers above or below. And this describes the volume of water added per unit time per unit volume of the aquifer, with units of R being volume over time times volume. And this specific storage, S sub S, is the volume of water added to or released from storage per unit volume of aquifer per unit change in hydraulic head. And the units of specific storage are volume over volume times length. Okay, so now if we use the law of conservation of mass, so tailored to our scenario, it says that inflow must equal outflow. So stuff going in equals stuff coming out. So what we mean by that is the flow into the right face plus flow introduced from an external source must equal the flow across the left face plus any change in flow due to storage in the medium itself. So mathematically, we can write this statement this way as equation 2. And if we rearrange to put the Q terms on the left and move the R term over to the right, we get equation 3. And if you use Darcy's law with hydraulic gradient being the rate of change of H with respect to X with a minus sign up front, we can update our flow equation 3 as follows. So what we get is this expression 4 here. And then if we divide through by K times A times delta X, we get expression 5. And then if we let delta X and delta T go to 0 and 5, we get the one-dimensional groundwater flow equation 6. And if you, excuse me, if you're familiar, this looks like the heat. This is essentially the heat equation. Here, equation 6. In the scenario of groundwater flow. And here we've introduced hydraulic diffusivity K by means of K is defined to be hydraulic conductivity K over specific storage S. Okay, so one way to illustrate groundwater flow is by means of a physical groundwater flow model. So we have a picture of one of these to the right here. And a groundwater flow model, or sometimes it's called a sand tank, such as the one pictured in figure 4, we got this from Ball State University's Department of Geological Sciences. These are educational devices constructed of sturdy layered sand lenses to represent a sliced section of earth. And through the use of water tinted with food coloring or grape Kool-Aid, it's possible to observe a wide range of groundwater movements. And the sand tank is designed so that water can flow between narrow rectangular columns on either end into or out of the aquifer portion in the middle by means of small holes at the base of each column. Okay, now groundwater flow models are not specifically designed to measure wellhead levels, but we were able to physically simulate one-dimensional groundwater flow through an aquifer with fixed head levels at each boundary with the available sand tank. And we did this by, pouring a green food color water at a fixed rate into the column at the right end of the sand tank and allowing the water to drain out through a flexible tube connected to the drain hole at the left end of the sand tank. And so this figure 5 shows a screenshot. We used a physics software called Tracker that you can use to take a video of something moving and then look at individual frames and track the motion of the object. So we use Tracker to analyze a video that we took using a cell phone of the sand tank and collect wellhead levels from 3 wells. There's 3 wells here. That's the left well, that's the middle well, and that's the right well. And what you should see, there's a pink, green, and red colors there as we're checking each frame and looking at the height of the water frame by frame. Okay, so this figure 6 here provides an illustration of our sand tank aquifer. And a mathematical model for one-dimensional groundwater flow through this aquifer consists of the groundwater flow equation 6 that we just derived, along with appropriate boundary conditions and an initial condition. And to simplify our model, we're going to assume that there's no recharge term in equation 6. And so the initial value boundary value problem that describes this specific situation is as follows. So equation 7 is our groundwater flow equation where we took out recharge. And then 8 and 9, those describe boundary conditions at each end. We have fixed head levels, H0 on the left and H1 at the right end of the aquifer. And 10 is our initial head level at time t for every point along the aquifer between x equals 0 and x equals a. In order to guarantee a solution to our initial value boundary value problem, we assume that initial head level x, f of x, is sectionally smooth on the interval from 0 to a. And by that we mean f has at most a finite number of removable jumps, discontinuities, and corners, with the function as derivatives being continuous between such points. Okay, so now we look at how we solve our model. So a standard way to solve an initial value boundary value problem like 7 through 10 is to write the solution h of xt as the sum of a time-independent steady state h of x and a transient w of xt. So what we mean by that is h of xt is written as h of x plus w of xt, where w of xt is defined to be h of xt minus capital H of x. Okay, so it follows that these functions on capital H of x and w of xt satisfy an ODE steady state problem and a PDE transient problem. And here's the steady state problem. It's the derivative, second derivative of h with respect to x is 0. H at 0 is h0 and h at a is h1. So if you integrate 13 twice and impose boundary conditions 14 and 15, you find that h of x is h0 plus h1 minus h0 over a times x. So it's a linear function. Okay, then here's the transient problem. So this is a partial differential equation with homogeneous boundary conditions and then an initial condition given by 20 there. So it's our initial head level minus the steady state solution we just found. And if you use separation of variables, what you'll find is the solution to this problem 17 through 20 is this series solution here, where the coefficients b sub n are given by integrating from 0 to a our g of x function from 20 and multiplying each g of x by sine at n pi over ax. Okay, if you substitute 16 and 21, our steady state and transient solution into 11, we arrive at a model for groundwater flow through an aquifer with fixed head levels at each boundary. It was given by equation 23. And so now, if you want to test the model, we need to choose an initial head level distribution, calculate these coefficients b sub n, establish model parameters, and determine the number of terms to keep in our series solution 23. So for initial head level distribution, we're going to choose a linear function. So f of x is alpha plus beta times x, where alpha and beta are determined from the initial head levels measured at each of the 3 wells. And for the coefficients b sub n, we use 22 along with 20 and 24. And you can actually calculate this integral here, and what you get is 25. You get a nice formula for each of the b sub n coefficients in terms of alpha, beta, h0, and h1. Now, for our sand tank aquifer, the length of the aquifer is 23.75 inches. And the boundary head levels at the left are 0.5625 inches, and at the right are 9.6875 inches. Okay, so if you use Mathematicus fit command, which is going to perform a least squares fit, we find that for our initial head level distribution, alpha is 1.2454 and beta is 0.021101. So then if we did a graphical mean square error comparison between our initial head level distribution f of x and our model h of xt at time t equals 0. And what we find is that a partial sum of 25 terms in 23 should be sufficient. There's a picture of our model, which is the red curve, and our initial head level, which is the blue line. Okay, now we don't know what type of materials in the aquifer, but we suspect that it's comprised mainly of some type of sand. So we're just going to choose a value for the hydraulic diffusivity K to try to produce a good graphical fit. So you can pick values of K to get the graph, the curves to line up with the points. And then after that, we just use the Mathematicus find minimum command to minimize the sum of the square errors. And so what we ended up getting with K is 8.8526 inches squared per second. We got a root mean square error of about 0.7840 inches in. And if you look at the model is the curves and the data we collected are the dots. And it should be clear from figure 8 that there's a poor agreement between model and measured data. So then in order to revise our model, we considered several scenarios. We actually looked at 6 different scenarios. And one of them is to treat hydraulic diffusivity K as well as the boundary head levels H0 and X1 as parameters. And again, we started with choices of parameters to contain a good graphical fit, followed by an application of Mathematicus find minimum command to minimize square errors. And we find that with K is 17.3708, H0 is 1.8493, and H1 is 6.8853 inches. We get the result shown in figure 9 with a root mean square error of about 0.1069. This is I still find it this cool how nice the model works out here. Okay, so that's the original Simeo model that appeared in 2020. So now suppose that instead of boundary conditions that remain fixed for all time, the head levels at one or both of the boundaries of the aquifer can change with time. So that means the boundary conditions 8 and 9 are replaced with functions on the left and right ends of the boundary. So h at 0t is phi of t and h at at is psi of t for t bigger than 0. So we're now going to look at an approach to solve this new initial value boundary value problem. We have the same equation 7, the same initial head level function, and we have new boundary conditions 26 and 27. They're time dependent. Okay, so using the idea of splitting the solution h of xt into a steady state and a transient part from like we did before as a guide, let's write the solution as 7 with boundary conditions 26, 27, initial condition 10 as the sum of I'm going to call it a steady state solution in quotes, v of xt, and I'm going to call it transient solution in quotes, w of xt. So v is going to be, it's going to be phi plus psi minus phi over a times x, where phi is the boundary condition at the left boundary and psi of t is the boundary condition at the right boundary. And we'll define this thing we'll call the transient solution w of xt to be h of xt minus v of xt. Then with h of xt defined to be v of xt plus w of xt, one can show that w of xt solves the following initial value boundary value problem. And here S of t is 1 over k times, basically it's phi prime plus psi prime minus phi prime over a times x. Now, if you compare this new transient problem to the transient problem we saw before, we see that essentially the only difference is that there's a non-homogeneous term S of xt in 31. And so if you go back and you think about the idea of variation of parameters that's used to solve a non-homogeneous linear ordinary differential equation by writing the solution of the non-homogeneous equation as a linear combination of solutions with the corresponding homogeneous equation with coefficients being unknown functions to be determined, well, you can use the same idea for partial differential equations as well. So let's suppose that our transient, in quotes, solution w of xt is of the form of this sum here. And we'll write S of xt as this sum here. It's just a Fourier series for S of xt. So S of n of t are the Fourier coefficients for the S of xt function. So if you use the suggested form of solution 36 with Fourier series for S of xt, then it turns out that these coefficients a sub n of t are given by this integral here, where a sub n at 0 is 2 over a times the integral of capital G of x times sine of n pi over ax. And so we're led to a model for groundwater flow through an aquifer for the case of time-dependent boundary conditions. And it looks like this. So it looks somewhat like what we had before, except instead of having H0 and H1, we start out with these time-dependent boundary conditions here. And these A sub n coefficients are functions of time, and they're given by equations 39 and 40. That's how you calculate them. Okay, so now I want to test our new model, and so we need to consider a scenario for which we have time-dependent boundary conditions. And so here's three possibilities that we can use based on the setup of our physical model shown in Figure 11. So in Figure 11 here, here's x equals 0, and then and then over here x equals a. That's where we had the fixed head levels. But so now we have our left well, our middle well, and our right well. So what we're going to do is we're going to devise some ways to set up time-dependent boundary conditions at one or both boundaries. So here's some possible scenarios to test our new model. So the first one is on the x interval. So we start with the left well and go over to the right end of the aquifer. So let x sub l correspond to the left boundary and x equals a correspond to the right boundary. Then phi of t is going to be a function fit to the measured wellhead levels collected at x sub l, and psi of t will be set to the fixed head level at x equals a. And for this scenario, we set up the model on the revised x interval 0 to a hat, where a hat is a minus x sub l, and the revised well locations x sub m hat and x sub r hat, where you take x sub m and x sub r and subtract off x sub l. For the second scenario, on the x interval 0 to x sub r, the right well, let x equals 0 correspond to the left boundary and x equals x sub r correspond to the right boundary. Then phi of t will be set to the fixed head level at x equals 0, and psi of t will be a function fit to the measured wellhead levels collected at x equals x sub r. And for this scenario, we're going to set up the model on the revised x interval 0 to a hat, with a hat is x sub r, and the well locations will be x sub l and x sub m. And for our third scenario, on the x interval from the left well to the right, x sub l to x sub r, let x equals x sub l correspond to the left boundary, and x equals x sub r correspond to the right boundary. Then phi of t will be a function fit to the measured wellhead data at x sub l, and psi of t will be a function fit to the measured wellhead data at x equals x sub r. And for this scenario, we're going to set up the model on the revised x interval of 0 to a hat, with a hat is x sub r minus x sub l, and the well location for this will be x sub m hat is x sub m minus x sub l. Okay, so I'm going to start with the first scenario. I'm going to fit the data collected to the left well to a fourth degree polynomial using Mathematicus fit command. So here's the fourth degree polynomial. And we'll set the, that's phi, and psi of t is going to be the fixed head level at x equals a. And our revised interval and well locations will become 0 a hat are going from 0 to 20.5, and x sub m and x sub r hat are 8.75 inches and 15.25 inches. And so for our model, we're going to use Mathematica to set up a partial sum for our series solution 41 with phi and psi given by the equations on the last slide. And we'll need an initial head level distribution, which we choose to be a shifted version of f of x, which is f hat of x is f hat of x plus x sub l. And the coefficients a sub n of t are computed by means of equations 38 to 40, and k is a parameter that can be varied. Okay, so to determine the number of terms needed in our model, we're going to compare partial sums of our series solution 41 to the initial head level distribution for our shifted function f at time equals 0 seconds. And we use the graphical comparison as well as the square error comparison. We see again that 25 terms should be sufficient. And figure 12 compares our model to the initial head level. So our first scenario, starting with a choice of hydraulic diffusivity k that provides a good graphical fit, then minimizing a root mean square error between model and measured data at the two wells, we find that with k equals 7.54622 inches squared per second, we get a root mean square error of about 0.56 inches. And as we see in figure 13, while model and measured data are similar shape, ideally there should be a way to revise our model to produce better results. So in order to revise our model for the first scenario, like we did before, we're gonna let the head level H1 be a parameter by replacing boundary condition 43 with psi at T sub H1 is H1. And then we recompute our model with this additional parameter, we're led to the result shown in figure 14 with a root mean square error of about 0.11 inches. And here we have K is 17.8203 inches squared per second. H1 is 6.85774 inches. For our second scenario, we're going to choose initial head level distribution f of x given by 24 and set phi of t to be h naught, which is 0.5625. That's the fixed head level at x at the left end of the aquifer, and fit the data collected at the right well to a fourth degree polynomial with mathematically fit command. That's our psi function. For this scenario, revised interval and well locations become the aquifer length goes from 0 to 18.5 inches, x sub L is 3.25 inches, and x sub n is 12 inches. And so again, we use 25 terms in our model, start with a choice of k to get a good graphical fit and find k to minimize root mean square error between model and data. And we get 0.56 for a root mean square error when k is 206.7 inches squared per second. And as we see in figure 15, we sort of get a match for the right well, but not a very good match for the left well. So again, we're going to revise our model and let H naught be a parameter for the left well. And figure 16 shows we get a much better result with a root mean square of about 0.12 inches when K is 18.2 inches squared per second. H naught is about 1.8 inches. And finally, for a third scenario, we're going to revise our interval. So A hat's going to be x sub r minus x sub L, and x sub m is going to be x sub m minus x sub L. And for boundary conditions, we'll choose a B and psi to be the functions we fit to the data to left and right wells. We'll use the shifted function for initial head level. And for this model, we'll again pick 25 terms. And we have one parameter, hydraulic diffusivity K. And so we find root mean square error is minimized to about 0.15 inches with K is 18.59 inches squared per second. And we get nice results in figure 17. Okay, so in conclusion, using a sand tank groundwater model for an aquifer and collecting head level data by means of a cell phone camera and tracker, we've been able to show that the one-dimensional groundwater flow equation can be used to model the head levels in the aquifer for the case when there are time-dependent head levels at one or both boundaries. And the results obtained are surprisingly good, especially considering the fact that the aquifer we worked with does not have uniform material throughout. And here's some further questions we might consider, like how would adding a recharge term affect our models for the time-dependent head level boundaries? For the fixed head level boundaries, we tried this and we get essentially the same results as we saw. And is there a way to construct coefficients of the form 25 that would allow more efficient computation instead of computing definite integrals for each t value? Since we're integrating stuff, it's very computationally intensive to do these calculations. And our model assumes that the aquifer material is homogeneous throughout. So a natural question that could be considered in future investigations is, can we modify our model to take into consideration different materials in the aquifer at different levels? And the next 4 slides are just a bunch of references. Okay, so that's it. Thank you.